Today, I like to discuss Raoult's law of this vapor pressure. Before going to the Raoult's law, let me first explain what is meant by the vapor pressure of a substance. The substance may be solid and substance may be liquid. And vapor pressure of a substance I shall discuss very elaborately in the application of thermodynamics for general phase equilibrium. Today's lecture I shall try to limit the vapor pressure of a liquid. And if we take in a closed evaporated closed container, suppose it is evaporated closed container, and here is some liquid. Here some liquid. It is evaporated container at a given temperature, and the temperature may be controlled by keeping this container in a thermostat. Say temperature is T. So in a evaporated vessel, whenever the liquid is inserted, liquid is trying to evaporate from the surface of this liquid. And this evaporation, as the liquid getting evaporated, this vacuum will be getting filled up with these molecules of this liquid vapor. And here also we can place 1 manometer or pressure gauge. How much the pressure is developed by the vapor of this liquid over the surface. And whenever these molecules of this vapor is getting accumulated, these vapor molecules collide on the surface of this liquid, and it is getting re-entering into the liquid. This is vapor. So this is the evaporation, and this may be taken as the condensation. And at this start, the evaporation is a high. Rate of evaporation becomes high. But as these vapor molecules are accumulating, the condensation is also getting much more momentum. And this one is the evaporation, and this one is condensation. And after certain time, the rate of evaporation and rate of condensation becomes equal. So whenever these two becomes equal, this system we call to attain equilibrium. Liquid and vapor remains at equilibrium with each other, and at that time the vapor pressure shown by this liquid, is called the vapor pressure of this liquid. And this vapor is saturated vapor, as the vapor is remaining in contact with this liquid. So this vapor pressure is also called the saturated vapor pressure of this liquid. And at a given temperature, you can see this vapor pressure remains unchanged with the time. That means at equilibrium, that is the condition of this equilibrium. Whenever the equilibrium is reached, the vapor pressure of this liquid remains steady and will not change with the time. So the curve will be like that. Here the rate plotted y-axis and time plotted along this x-axis, and it is the rate of evaporation constant. Rate of evaporation is constant, and the rate of condensation starts from 0, and when time is 0, time of taking this liquid in this evaporated vessel 0, no vapor is found in this evaporated space. So this rate of condensation will start from 0 and it will increase. I am going to touch this, and this one is the rate of condensation, and this one is the equilibrium. At this time, the system attains equilibrium. Rate of evaporation and rate of condensation becomes the same whenever these two curves are touching each other. So the vapor pressure of a liquid, actually vapor pressure of a liquid depends on several factors. Vapor pressure of a liquid depends on one, nature of the liquid. Nature of the liquid. The liquid is having lower intermolecular attraction. This liquid will be more vaporized. And the liquid, as for example, say one is ethanol, and other is water. And intermolecular attraction of ethanol is less than the intermolecular attraction of this water liquid. So this liquid is more volatile. This one is more volatile, and this one is less volatile. So the vapor pressure at a given temperature of this ethanol will be much higher than that of water. The intermolecular attraction of this water is very high due to the hydrogen bonding, and you know each molecule of water is bonded by hydrogen bonding with these 4 water molecules. So water is very less volatile, and its vapor pressure is also low in comparison to the ethanol. And second very important is the temperature. As the temperature is increased, vapor pressure of this liquid is also increased. As you say, with the increase in temperature, the molecules of this liquid having more kinetic energy, and they have much more tendency to escape this liquid to the vapor phase, and the vapor pressure is increased. And very strikingly, we can say this vapor pressure of a liquid, vapor pressure of a liquid does not depend on shape and size of the container. Shape and size of the container in which this liquid has been kept. And second one, it does not depend on the surface area of this liquid. It does not depend on the surface area area of the liquid. This is very interesting to consider. As the surface area is increased, there will be more evaporation, but the vapor pressure, which is the thrust given by the vapors on the walls of the container per unit area, this will remain fixed. So these are all about the vapor pressure of a liquid. Now I am coming to the Raoult's law. Raoult's law of vapor pressure. Let us take one liquid here. It is the vapor and it is the liquid. Liquid, say one liquid, first liquid, and the vapor pressure of this liquid is in pure state P1 naught at a given temperature. So plus another liquid, if we consider say liquid 2, here it is liquid and here it is vapor, and the vapor pressure is suppose P2 naught. And whenever these two different liquids are mixed up and forming a solution in which both the liquids are volatile, then we get a mixture. We get a solution of the two volatile liquids, and this is the liquid phase A plus B, or 1 and 2, both the liquids are here, and it is the vapor. Since both the liquids are volatile, so vapor will also contain the liquid first component and second component both. And the pressure, the partial pressure, now it becomes a partial pressure. P1 is the vapor pressure of the first component, and P2 is the vapor pressure of the second component, and total vapor pressure is equal to P1 plus P2 at the same temperature, and it is the solution of two volatile liquids at a given temperature. Whenever these two solutions are being mixed up, then the randomness of the molecules in the liquid phase is increased. With the increasing randomness, the chemical potential of this liquid is also decreased. So majorly the escaping tendency of the liquid molecules of each component from liquid to vapor is also decreased, and so this P1 must be less than P1 naught, and similarly P2 must be less in P2 naught. These are the vapor pressures in pure state of these two components 1 and 2. So how we can get P1 and P2 of the two components whenever they are in a solution? Here Raoult's law states at a given temperature, at a given T, this P1 is proportional to X1. X1 is the mole fraction of the first component in the liquid phase. As there is more and more mole fractions of the first component in the liquid phase, the chemical potential of the first component in liquid phase is also more, and so more escaping tendency to the vapor, and vapor pressure is also increased. More evaporation and more vapor pressure is also found. And so P1, you can write this K1 into X, K into X1. K is the constant, or K1, I can write as K1 also the proportionally constant. K1 could be obtained by the following way: when X1 equal to 1, X1 equal to 1 means a pure 1, pure first component, pure first component. Then when P1 is equal to P1 naught, putting here P1 naught equal to K1. So the Raoult's law for the first component now becomes, putting the value of K1 equal to P1 naught, we get this P1 equal to P1 naught into X1. This is the equation number 1. So the Raoult's law can be stated as, at a given temperature, the partial vapor pressure of a liquid, of a component in a liquid mixture is a product of the partial pressures, is the mole fraction of that component, and the vapor pressure of that component in pure state. Similarly, P2, in this way you can write P2 naught and also X2. If we like to express this P2, if we like to express this P2 in terms of this X1, then this is 1, and P2 equal to, and P2 naught into 1 minus X1. As you know, X1 plus X2 equal to 1 for this binary function. So we can write this one equal to, or P2 equal to P2 naught minus P2 naught and X1. And the total pressure, this is equation number 2. And the total pressure P equal to P1 plus P2. It is the Dalton's law of partial pressures. Sum of the partial pressures becomes is equal to the total pressure in the vapor obeys the ideal gas equation. So writing, substituting P1 and P2 from this equation number 1 and from equation number 2, we get P equal to P2 naught plus P1 naught minus P2 naught into X1, and this is equation number 3. So this is the P1 partial pressures of the first component, partial pressures of the second component, and it is the total pressure, total vapor pressure over the solution, over the solutions of two volatile components. These three equations we can show by means of a graph. So this is the graph. Say here X1 here X1 is 0. 0 means a pure second component, and here X equal to 1 means a pure first component. So if we draw, temperature is fixed, temperature is constant at a given temperature. We are drawing this graph. Here the VP, vapor pressure, and if we draw the equation number 1, P1 P1 equal to P1 along this y-axis and x1 along this x-axis. So this equation will be y equal to mx. So y equal to mx, it will start from origin and will give you a linear relationship, and here it is a P1 naught. When x1 equal to 1, so P1 equal to P1 naught. P1 naught is the vapor pressure of this first component in pure state. And let us consider this P1 naught is greater than P2 naught. Means the first component is more volatile than the second component. Then for the equation 2, it is equal to y equal to c minus mx. If we plot a P2 against x1, and P2 naught is fixed at a given temperature. If the P1 naught is also fixed at a given temperature. So this can be started here. It is P2 naught. When x1 equal to 0, P2 equal to P2 naught. So when x1 equal to 1, P2 naught, P2 equal to 0. So it will go like this way. This is P1 and this is P2, and this P here, P is plotted along this y-axis and x1 is plotted along this x-axis, and P1 naught is greater than P2 naught as we have assumed. So this one also positive. So this curve will start from P2 naught and ends at P1 naught, and this is P equal to P1 plus P2. At any concentration, suppose here it is the concentration, it is P1 and it is P2, and sum of the two will give you this total pressure P. Raoult's law is very important, though it is valid only for the solutions, for the ideal solutions. Ideal solution means when the components, the molecules of these two components are totally having the uniform intermolecular attractions or uniform cohesive forces, and the action of or the activity of one component will not be affected by the other component. Means each component will behave ideally, and then we will call the situation is ideal situation and the solution is called ideal solution. Actually, Raoult's law is valid strictly for the ideal solutions. Or we can say, like the definitions of this ideal gas. Ideal gas is that gas which obeys the PV equal to nRT equation. So one equation will justify the or having a characteristics of this ideal gas. Similarly, the Raoult's law also characterize the ideal solutions. Means ideal solution is that solution which is in which the Raoult's law is obeyed in all composition of the solutions and at all temperatures. So this Raoult's law is Pi for the ith component is Pi naught into Xi. This is the Raoult's law. And Raoult's law could be verified. Raoult's law could be derived thermodynamically very easily. Thermodynamical derivation. Thermodynamical derivation of the law. Very simple. Say here the liquid solution, here the liquid solution, and here the vapors, here the pressure P and temperature T. So at a given temperature pressure, this liquid solution remains at equilibrium with its vapor. Each component in liquid phase remains in equilibrium with that component in vapor phase. So we can write the mu I, chemical potential of that component in the two phases will be the same. Mu I liquid is equal to mu I vapor. Since the chemical potentials are the same for the two phases when they are in equilibrium. Instead of write this one, I can write mu I naught liquid plus RT ln xi. Xi is the mole fraction of the ith component in the liquid phase, and this one equal to mu I naught in vapor plus RT ln P1. P1 is the PI. PI is the vapor pressure of this ith component in the vapor phase. So this is the main relation, suppose relation equation number 1. If we find a relation between this one, this standard value and this standard value, then when we can do whenever xi equal to 1 means pure ith component, then Pi equal to Pi naught, vapor pressure of the ith component in pure state. So substituting here this mu I naught liquid plus xi equal to 1, so ln1 equal to 0, and this one equal to mu I naught vapor plus RT and ln. Instead of Pi, I shall write Pi naught. And if we put this term here, substituting this term by this part, then this one will be cancelled and it becomes RT ln xi plus RT ln Pi naught equal to RT ln Pi. This one is substituted here. So mu I naught vapor will be cancelled. So RT ln xi plus RT ln Pi naught equal to RT ln Pi. So cancelling RT, we can write also RT ln here xi into Pi naught equal to RT ln Pi. Cancelling RT and ln, we get this Pi equal to Pi naught into xi. We get this relation. So this Raoult's law having a thermodynamic basis, and from this thermodynamic principles of concept of this chemical potential, it could be derived. Now I can give one problem. One thing is that here this xi is the mole fraction. Xi is the mole fraction of the ith component in the liquid phase. If we try to get this mole fraction of this ith component in vapor phase, then this mole fraction of the ith component in the vapor phase is say yi. Then in that case, this yi, according to the Dalton's law, partial pressures, yi equal to pi divided by total pressure. And this instead of pi, we can write this pi naught into xi and divided by total pressure. So yi and xi is related by this way. And we can give one problem. So far we have related the following relations. This P1 equal to P1 naught into x1, equation 1, and P2 equal to P2 naught into P2 naught plus P1 naught minus P2 naught into x1, and total P equal to P2 naught into x1, and total pressure P equal to P2 naught plus P1 naught minus P2 naught into x1. And the mole fraction of the height component in the vapor phase is equal to the partial pressures of this vapor phase and divided by the total pressure, and this is equal to xi into pi naught and divided by total pressure. This is equal to yi. And the problem is that at 20 degrees centigrade, the vapor pressure of a benzene and toluene are 74.7 torque and 22.3 torque respectively. And our task is that a certain solution of a benzene and toluene at the same temperature, same T, has vapor pressure equal to 46.0 torque. Find the benzene mole fraction in the solution and in the vapor above the solution. Above the solutions. So this is the problem. At 20 degrees centigrade, the vapor pressure of benzene and toluene are given, this one and this one respectively. A certain solution of benzene and toluene at the same T, means at 20 degrees centigrade, has a vapor pressure equal to 46.0 torr. Find the benzene mole fraction in the solution and in the vapor above the solutions. So in this case, the total vapor pressure is like this, and this equation we can substitute here. 46.0 equal to, and P2 say for toluene, it could be written as P toluene naught plus P benzene naught minus P toluene naught into X benzene. So this one toluene, in case of toluene is 22.3 plus, here it is 74.7 minus 22.3 into XB. XB, the mole fraction of the benzene in liquid phase. So XB, you can calculate XB, you can calculate, and it will be 0.045. And then the next one is the mole fraction of benzene in vapor phase, means YB equal to XB into XB into PB naught and divided by total pressure. And this one equal to XB, we have obtained 0.45. We have got this one, and this is equal to 74.7 torr and divided by, and P is the 46.0 torr, and this one gives you the value 0.73. This is all about the Raoult's law of vapor pressure. I have defined what is meant by the vapor pressure of a liquid, and what are the Raoult's law, and I also give one calculation to show that the vapor pressure, the mole fraction of a component in liquid phase and also in vapor phase. In my next class, I shall discuss the ideal solution and non-ideal solution in the chapter of the thermodynamics of two-phase equilibrium. So thank you all for watching this video, and I think if you like, then please subscribe. Okay, thanks.